All right. Hello, I'm Alex Algitz, and I'm looking at this kind of machine learning model calibration study from these people from Europe. So that's fun. So kind of the idea behind the paper is there's a bunch of computational models that are kind of predicting drug target interactions. And these are theoretically going to be really useful for drug development. We make them, they're super cool. However, a lot of the models are poorly calibrated in terms of uncertainty. So kind of the idea is if your model says it's 70% confident that, this is going to be that, and in reality it's 90 or it's 50% confident or it's 50% chance that this is going to be that, then that's bad and that's calibration error. And that means your model is inaccurate and you can't really trust it at the end of the day. So these certainty errors, they can happen for a lot of reasons, but what the paper is really worried about is how can we reduce this error instead of how can we address this error from like a root cause of the models. Um, so it looks at a couple different enzymes throughout the body, and then they're first gonna look at hyperparameter tuning methods to try and avoid overfitting, and then they're gonna go into uncertainty estimation calculation to kind of make sure we can trust that final number that it spits out. So they look at a couple different hyperparameter kind of choosing methods, and it turns out that binary cross entropy loss is kind of consistently the best performer for these. So that's kind of what you should look at. And then this graph, the top row is calibration errors, so lower is better. And then the BS is kind of like a checking our work score. And the AUC is area under curve, which is kind of a classic. Um, and then the method to find uncertainty or the calculation for uncertainty that they found is this Hamilton Monte Carlo Bayesian last layer method. They call it HBLL. So that's kind of like if we have a bunch of marbles and we throw them in the air and kind of track them, but we already kind of know where they're going. Once they're done moving, we can keep kind of the best, 10 or 12 marbles, and then we can kind of think about these good marbles. That's kind of the general idea behind this HBLL um, method that they use, if that makes any sense. So the HBLL compared to the other methods that they tested, this MLP thing, it generally does pretty well, and I think it's like a little faster for computing time and just like a little more convenient generally. So we like this HBLL method because not only does it do well, but it also outputs kind of a range of predictions that it gets from multiple samples. So essentially we're asking, okay, is this 70% number that we're getting, is this like an average that's from like 30 to 90? Or is this a bunch of tight like points that are right around 70? And so if we have those like tight um, like a tight variance, then we can be more confident in the model's confidence. So this is good because we can check our model and then it's more applicable in real life settings that our model will be used. So yeah.